So I showed you, some of these things that we have been doing in developing these networks. And one example is we use, the question is how you define how a molecule looks like. And I, mentioned we use the structural group analysis is one way to do it. Now what we do is we use we use language models. Actually, we use the same model that's used for ChatGPT to understand the name of a molecule and also an entire reaction, which is nothing else than a language, right? And so that's all new. That's a paper that we're just in the process of submitting, which is quite interesting. This here I want to show you because I think it's really intriguing. I mean, that's a technique that we have been working on for a while, and I'm not sure where it's going to go, but it's a very intriguing concept. So this is here what's called generative adversarial networks. That's kind of the opposite of what I showed you so far. What I showed you so far were very simple networks. This here is what's called deep learning, is using many layers, many neurons, and very, very complex deep learning networks. So we use these to generate models to close these terms in the equations that we want to solve. So here, for example, you have the momentum equation, the mean momentum equation, or mass fraction equation, and they have terms which are unclosed. Here, for example, these transport terms. And usually we use here something like a Smagorinsky model. And but now, this is the definition of the term. Let's say I have the DNS, kind of resolution. I could actually evaluate these terms analytically. So the idea is to say we use LES, and LES gives us here the resolved field, but it does not give us, the subfilter field. And then we use machine learning to reconstruct the unresolved part. And then we have kind of a DNS resolution, and we can, just evaluate these terms. Here, so that's the idea. We have this is the solution of an LES, let's say, and then we use an upsampling here, or we use a what's called super resolution technique that makes us from LES make something like this, and then we can use this field to resolve these terms, plug them in the equation, and then get the next time step of this field. And right, so this is what people have used here in computer graphic. You see this cat here, and you see is a kind of pixelated. But somebody trained a network that has seen a lot of little cats, and higher resolution, and then you super resolve. The network then gives you this, and you see here these hairs, and all the structure is a lot better. This is like you watch the movies, and there's you see on some security camera, somebody was walking there, he had glasses, and you see the reflection of the glasses. You see another guy who had glasses, and then you see the murderer, and this, and then they say, hey, can you super resolve this? And they go like, oh, you see in the eye, of reflection of the eye, you see who the murderer is. So that's kind of what we are trying to do here. So, so this is an example. This is a DNS, and then we filter the DNS, you get this, and then the question is, can we also here train a network so that we can recover this? And that's what we are doing here, for example, with a convolutional neural network, CNN. These convolutional neural networks, they're nice because they don't predict one point, they predict a field. And predicting a field means you get gradient information and so on, like this. So that's what we do. We take a DNS, we filter the DNS, and then we train a network to give us back the DNS resolution. Okay, so that's that's just a supervised learning, and it turns out that's okay, but it's not really good. Okay, so what we do then, we use a second network, a second network, and that network we show the network
pictures either of the real DNS or of a fake DNS, you know, a picture that was really an LES and was generated here by our neural network. I call this a fake image, right? So we show the discriminator, so the second network, we show it either a real image or fake image, and the discriminator does nothing else than tell us this is a real image or fake image, okay? So, okay, but now the trick is, now we let these two networks play against each other. That's what's called the adversarial. So it's a generative network because we use a generator, and it's called adversarial because these are playing against each other now. So we have a new image. We show it to the discriminator. The discriminator says it's real or fake, and depending on what the discriminator says, we feed that information back to the generator and said, hey, this image wasn't really good because the discriminator spotted, you know, that it was fake. Or we say, this was a really good image because you just tricked the discriminator. At the same time, you know, once the discriminator has an answer, we tell the discriminator also, this was right or this was wrong. So in the training of the discriminator, he is on the fly, and while the generator gets better and better, also the discriminator gets better and better. And so you know, I always say this leads to infinite intelligence, infinite artificial intelligence. Of course, it does not, but it turns out that this adversarial process here really makes the networks better. We have a loss, so in training networks, you always define a loss function. You try to drive the loss function to 0, which would be no error. And that's the training process. So here we use pixel loss. We just compare, in the training, we compare the fake image with the true image, and you know, pixel by pixel, and it gives us an error. We also evaluate gradients, which gives us another error. And what we do is we evaluate continuity on this. Of course, the DNS satisfies continuity. After we generated the fake image, we evaluate continuity on this, and it also contributes here to the loss function. So we call this a physics-informed training because it will satisfy continuity at the end of the day. And of course here again the generator loss function also has information from the discriminator. Okay, so this here is maybe we don't need to discuss this here in detail. This is all about the training process, how this is done, and this is some result here. This is the velocity gradient statistics. So we are interested in gradients, and so these are velocity gradient statistics. We didn't talk about it when we talked about turbulence theory, but it's well known that so this is kind of a Gauss function, but if you, for very large gradients, positive and negative, for very large values, it becomes has exponential tails. That's why in this log plot here, you know, this is this kind of linear line. And then here, this is the filtered DNS. And you see the large gradients are gone. This is the filtered DNS. And then this here is just, the green line is just using the generator. I mean, just train a CNN type network. And you see it also misses out on some of these very large gradients. And then here the model I just showed you. So by the way, red is the DNS. That matches the DNS really well, and this is the energy spectrum, and also here it matches really well, except for the very high energy content. This is how the structure of the network looks like, and I think the bottom line here is just it's very, very complicated. And we didn't come up with this ourselves. We just take what here these guys from computer graphics, or image processing, whatever they call it, what they have developed here. This is it's called an enhanced super resolution generative adversarial network. That's something from the literature. And we have made small modifications to this
anytime we see it doesn't work, you can think of why does it not work and then make modifications. But in general, that's what it is. And here's an example. This is the DNS. This is the filtered DNS, and then super resolved. And you see, it looks really very much like this. And there's a lot of features which are lost here, really, which were recovered again in this super resolution. So, for example, you have this very thin structure here, which here is totally gone. But then here, the super resolved, it's back. But these are, of course, just images. I mean, whatever, I can tell you whatever I want. But what's really interesting is now we take the super resolved image and now we evaluate the fluxes, because these are really the quantities of interest. That's what we want to know. And so here, you see this is Smagorinsky, dynamic Smagorinsky, and this is the model. This is from the DNS. And you see, it's around this right value, but it's not super good, let's say. And this is the super resolution model, and that's actually much better, let's say. It's not perfect, but it's much better. And then, so that's what we call an a priori test. You evaluate the modeled quantity from the DNS, and you evaluate the modeled quantity from your model, and then we compare it. That's an a priori test. A posteriori test means we plug the model actually in a simulation, and then we see how it performs in the simulation. And this here shows the result from an a posteriori test with not just a simple super resolution GAN. This is what we call a dynamic mixed super resolution scale similarity model. Okay, so and the name GAN doesn't even it's adversarial also. So this is decaying isotropic turbulence. This kinetic energy of isotropic turbulence, it decays in time, and the DNS are these symbols here, or the filtered DNS are these symbols, and then I can solve the momentum equations. Is all without reactions. I can solve the momentum equations without a model. I get this, and with the scale similarity model, I get this one here, and then with a what is this? Super resolution scale similarity model, I get this, and this is the model. Actually, the final model is dynamic mixed super resolution scale similarity model. And that's actually not so bad. And what it does is while doing this, we have seen that certain features this thing can predict really well, but it turns out other features it cannot predict well. I mean, for example, if you train the network with a certain ratio of filter size over flame thickness, and you apply it to a different ratio of filter size over flame thickness, it's all bad. Okay, and so so that's what this then covers. So we have extended this model to become independent then of parameters like this. Anyways, that should just show an example. Here's the energy spectrum, and also here you see model is not so bad. Okay, so this I just want to show at the end because I thought it's a neat thing. And again, I mean, we'll see where these things go, if they will ever be at a point where you can use them, or if not. I mean, you can imagine that using an ANN like this also is not so cheap. So maybe today it's still too expensive. Maybe in 10 years from now, we'll all do computation on GPUs anyways, and then, these networks, they're really good on GPUs. Okay, good. So that's all I wanted to say about machine learning. Any questions about this? While I switch slides. And then maybe I don't have too much time for this now. 45 minutes, right? Yeah. So, and then last focus topic here is hydrogen. And again, this is kind of a nice example for why, for many of the things that we have discussed in the past few days. Hydrogen. So why hydrogen? This is here energy policy meeting. And the question is, before I ask the question, can anyone anticipate the answer? The answer is hydrogen. You know, it's kind of the solution to all the energy problems we have now. It could also be, somebody else maybe would say electrification. And I have another version of this plot here, of this cartoon, where this guy says hydrogen, and this guy says machine learning. You know, that's so anyways, I mean, you know, hydrogen is interesting to talk about these days. Anyways, I have told you why hydrogen is interesting. I don't think I need to talk about this much more. Hydrogen is interesting in terms of combustion, because anytime we do combustion, we have a multi-objective optimization problem. In combustion, always at least stability, emissions, and efficiency need to be optimized at the same time. Typically, also this cost. Cost is something here in the center. You know, I'm a scientist. I don't worry about cost. You know, I just try to think about these three. And very often, if you improve efficiency, the other two get worse. I can give you many examples in combustion how, you know, one. Yeah, I mentioned this a few times. In lean premixed stationary gas turbines, or in stationary gas turbines, you try to burn lean premixed, very lean because of emissions, but that cuts down on efficiency, on stability. Diesel engines have particularly high efficiency, but bad emissions, you know, and so on. So there's always a trade-off between all of these. Now, hydrogen has a few good opportunities. There's no carbon, so there's no CO2, no soot, no unburned hydrocarbons, no CO. There's only NOx that's left over. If you have only one pollutant, it's much easier to deal with it than if you have many. You know, you can get high efficiencies in engines. I mentioned this before because, you know, of the ignition properties. And then you can also, you have high flame speed that can give you high stability against blow-off. At the same time, there are challenges. The high flame speed also can lead to flashback. NOx is an issue always. Safety is a big issue here, detonation, self-ignition. And what's interesting also, I'll show you the combustion characteristics of hydrogen are very complex. And that means at this point, I mean, at least for previous combustion, we can't really predict it, which means computational engineering gets very difficult. That's a challenge also. Okay, so what is different about hydrogen? I'll show you some properties, and then I'll show you two examples why, you know, what's different about hydrogen. Hydrogen here, heating value, which is energy per kilogram, is super high. It's actually, you know, I mean, much, much higher than any other fuel. So methane here is supposed to represent natural gas. Isooctane here is supposed to represent a liquid fuel like gasoline, just as examples. Energy density is super bad. Look at 30,000 versus 10, you know, because hydrogen is gaseous. I mentioned this before. There are two ways to store hydrogen. One is cryogenic at 20 Kelvin. That's super cold, in case you don't know the Kelvin scale all that well. That's very, very cold. And then, or pressurized at 700 bar, let's say for mobility. But even at 700 bar or at 20 Kelvin, the energy density here is about 6,000, and isooctane has 30,000. I mean, that's still a factor of 5 less than the liquid fuel, even at these conditions, okay? And that doesn't even include the tank here. I mean, that's just, you know, the hydrogen itself. Okay, so that's a big issue. And then, you know, there are other things here. The adiabatic temperature is a little higher, so you could imagine that NOx is higher. And then the Lewis number. I mean, that's the big point. The Lewis number is really low, and that will lead to interesting stuff going on. Now, you talk about premixed combustion, non-premixed combustion. I would say non-premixed combustion for hydrogen is easy. Why? This is because hydrogen is very reactive. It burns very fast, which means typically the Damköhler numbers compared to some other fuel, Damköhler numbers are much, much higher, which means the chemistry is much, much faster. which means, simple flamelet models like we just discussed, they are very often very good. And so this here shows an example. This is also a simulation that we did long time ago here in the 90s. This is a turbulent hydrogen jet. And you have measurements here for different species. And then you see the lines are, this is along the center line, and the lines are the simulations using, just here an unsteady flamelet model. And I mean, these species that are predicted really well. And then this is here OH, mole fraction temperature, also predicted quite well. This here is more mixing than the chemistry model. And then we can look at NO. And you see NO here, this is, if we would take NO just from a steady flamelet model, this is, much higher, 5 times higher. So that's wrong because we never, for NO, we never reach equilibrium. That's what this unsteady model here does. And so the model here gives you about this. It's very close to the data, and probably the difference here is more the chemical mechanism, which here in the 90s, wasn't as good as it is today. Okay, so let's say, non-premixed combustion, check, is not so complicated. And if we look at premixed combustion, things are different. And so I want to show you, why does hydrogen burn so fast? And, why is this important here? Or how important is the impact of these instabilities that we have also discussed before? Let me first show you 2 more things here about, properties. Maybe that slide was in the wrong position. 2 more things about properties. This is an experiment here that we did in a household burner. This is, let's say, a natural gas household burner. You have the cylindrical burner is perforated. The fuel air is mixed inside this thing and comes out through these holes, and then there's a flame here around it, and then on the outside here these coils, they carry water. So you use this to heat up the water. The gas actually flows in between these coils to heat up the water. And we used this, we took this out, and we covered most of it so that only a little piece is sticking out. Why? Because we used it in class, just as demonstration, so you want the thermal power to be not as high, and then we run this. And here you see it running. And what we do now is while we run it, so it runs on natural gas, but then we blend in some hydrogen. And you see here how the hydrogen content goes up. And you see while the hydrogen content goes up, you see this thing, you hear it also. You see this glowing. And then bam, all of a sudden you have flashback. What happens is the wall, heats up, and then on the inside of the wall, it doesn't even go through these holes. On the inside, it just ignites. Hydrogen wants to ignite close to a hot wall. So here's another one that we did in the same burner. We actually measured NOx in this burner for different compositions where hydrogen here also has been added. And what we found was that if we add hydrogen, we thought we should get more NOx, but it turns out we get less NOx. Here's methane, is 13 ppm, and hydrogen is not much less, but it's a little less. And that's interesting. So we measured the temperature to try and see what happens with the temperature, but the temperature was exactly the same. And then, we did a simulation, we analyzed it. And what you see then is this is the NOx that's formed. This is prompt NOx. This is from NNH, thermal NOx, and here through N2O. And if you add hydrogen, first of all, the flame burns faster. And because it burns faster, it goes closer to the burner, so you have more heat losses, which is why in this particular burner, the temperature is not higher, even though the adiabatic temperature would be higher. And so you don't get more thermal NOx. But that's a special thing about this burner. But then, of course, if you have, if prompt NO here is so important for lean hydrogen flames, for lean methane flames, and you have more hydrogen, less carbon, then you get less prompt NOx, and that was the reason why we get less
NO. So there are interesting things happening. Now, the hydrogen has super high flame speeds, and the question one could ask is, why is flame speed so high? This is how we measure the flame speed. I showed you this before. Here's a spark in the center. You get this spherical flame. And then, it's sparked here. This shows the burning speed as a function of stretch. And then this slope here is the negative Mach-Lehmann length, right? That's what we said earlier. And here, smaller curvature gives you faster flames. High curvature gives you slower flames. This is for methane. This here shows now an experiment for methane and for hydrogen, next to each other. And you see hydrogen is faster, it's a lot faster. And what you see also is that here the surface is always nice and smooth, and here very quickly you get these instabilities on the surface that, then also, make the flame even faster. So the question is, why is it faster? There are three reasons why it's faster. The first is even the unstretched burning velocity, is higher. Then secondly, there are curvature effects that just lead to the fact that this spherical flame burns faster. We said for methane, it becomes faster when the curvature goes down, but hydrogen, actually positive curvature, makes it faster compared to the unstretched flame. And so just curvature effects make it faster. And then third, you get these instabilities. We can look at these one by one. This here shows, again, laminar burning velocity as function of the equivalence ratio for hydrogen, for methane, and you see, this is an order of magnitude more. And then here, just as a reference, we talk a lot about ammonia these days. You look at ammonia, that's an order of magnitude less, okay? So these are big differences. So, at stoichiometric conditions, turns out hydrogen is 6.5 times faster than methane. And I could ask the question, what causes this? There are three effects I can think about. Number one, you have a transport effect, okay? So the Lewis number is much higher, and you would think if the Lewis number, if it diffuses faster, also the flame should be faster, okay? And that's true at stoichiometric conditions, but it turns out if you look at lean conditions, then the high diffusivity actually makes it slower. Okay, so here, we looked at just, and here with this FlameMaster code I gave you, you can very easily do these things. You just set the Lewis number equal to 1 of hydrogen, and you can look at the differences. If I set the Lewis number equal to 1, not equal to 1 is 40% faster. So at stoichiometric, 40% faster, but it, as I said, turns out for lean conditions, non-unity Lewis number actually makes it slower. Okay, so that's not the reason why it's so fast. And then second reason is thermodynamics, because you have a higher flame temperature. We saw earlier the flame temperature has a very strong effect. The adiabatic temperature has a very strong effect on the burning velocity. Okay, so here I did simulations where I just add a little bit of nitrogen to the fuel to make the adiabatic temperature the same as for methane. Okay, and then that makes a difference of 27%. But this is much higher. So the rest must be chemistry. Okay, radical balance. That I just say makes all the rest. And if we look at, this we discussed, all of this we discussed, and you can very easily see what makes it so fast. If you look at methane, of course, you see, you know this by now, methane consumption consumes radicals. CH4 takes 2 radicals, to be converted to stable intermediates. But if we look at consumption of hydrogen as a fuel, it actually produces radicals, okay? So, in order to burn, methane needs to be consumed, but that makes itself slow, right? But when hydrogen wants to burn, needs to be consumed, each time you consume one molecule, you made a lot of radicals. And so it makes itself fast, okay? So that's the real reason why it's so fast.
It's a chain branching fuel consumption. Okay, so that, you know, is nothing new for you. You know, this you learned all, you know, in the past few days. Here's, I mean, if you're interested in hydrogen premixed combustion, or let's say laminar flames, we just wrote a chapter here in a book that was edited here by Professor Tingers. Hydrogen, no, what's the title of this thing? I don't know. But the chapter in this book is on laminar hydrogen flames. It discusses a lot of these things. This is one figure from this book, and this is also very interesting. We said below 1,000 Kelvin, you know, all radicals should be gone. Okay, that was for methane. Here, so this is flame structure of a hydrogen, stoichiometric hydrogen flame. And you see here, this is the temperature. Look at the temperature. And, you know, this is where the temperature is almost zero. And look at where the radicals are. The hydrogen radical goes to zero at this point where the temperature is nothing. I mean, it's 300 Kelvin, a little more than 300 Kelvin. That's very interesting because in the fuel, you know, it doesn't consume radicals, it produces radicals. And then the second thing that's very interesting, shouldn't you get at low temperature chain breaking because of O2 plus H goes to HO2, right? And this is exactly what happens here. You see, this here is the heat release, or this here is HO2. And you see the hydrogen, when it goes away, it forms HO2. But that's a heat-releasing reaction. And you get a lot of heat release here at temperatures of, you know, roughly 300 Kelvin. That's where, so the temperature goes up, not only by heat transfer from downstream, it also goes up by H radical diffusing upstream, recombining with O2 to release heat. Okay, isn't that interesting? I mean, that's a heat transfer, that's a preheating mechanism that comes from the radicals, right? The hydrogen radical diffuses very fast. Hydrogen radical has a Lewis number of 0.17, roughly, let's say 0.2. So that diffuses 5 times faster than the heat, okay? So this diffuses 5 times faster here, but it carries the energy of a radical with it and releases it as thermal energy. Very interesting. You guys don't seem to be excited. I think this is really, really exciting. Wow. You should say, oh, wow, you know? Great. Okay, tonight you think about it and maybe you know, at some point you will feel the excitement. Anyways, so that's the chemistry effect. And now we have here the effect of Markstein length. We said the negative slope here, that's the Markstein number. There's a negative slope, so positive Markstein number, right? This is the same experiment for hydrogen, and you see it has the opposite slope. There's positive slope, the negative, so you get a negative Markstein number. And if I put a negative Markstein, positive curvature, negative Markstein number gives you positive effect, so this makes positive curvature burn faster, okay? So that, of course, will then lead us here to the here instabilities. Okay, so that's what we're going to talk about next. Why do you have instabilities? And we discussed this also. This here just reviews, again, why do you get hydrodynamic instabilities? You know, shown here in this picture. I showed you this picture before. And then why do you get thermodiffusive instabilities? So let me just say, I mean, just to remind you, hydrodynamic instabilities, they just come from the fact that you have a density jump across the flame front. And that front, the density jump moves in the flow field. And that creates an instability. You know, it has nothing to do with chemistry or anything. This is what's called hydrodynamic instability. It's just a density jump. And then the thermodiffusive instability comes from these Lewis number effects. And we said, this is positive curvature. I mean, let's say you have a disturbance like this on a flame. Here's burnt, here's unburnt. Disturbance like this is positive curvature. And we said for hydrogen, positive curvature moves faster. So after a while, it looks like this. And negative curvature moves more slowly. So after a while, it looks like this. And it shows you had an initial perturbation. and it grew with time. That's an instability, right? So, right, and so we discussed this, and this is the thing we haven't really discussed in detail. I think I showed you a dispersion relation which comes from a linear stability analysis, and it shows you if you have an initial perturbation at a given wavelength or given wave number here, what happens to it. This is the growth rate of the perturbation. And if the growth rate is positive, that's an instability, and the growth rate is negative, you damp out the perturbation, and it's a stabilizing effect. And you see two regimes here, you see two terms here. The first one is independent of Lewis number. You see this is always positive, okay? So that's the hydrodynamic instability. It's also called the Dareios-Landau instability, which is why we often use it as DL instability. And you see the growth rate is just linear with the wave number. And that will become important again. And then the second term here depends on Lewis number. If the Lewis number is larger than 1, this is actually positive, and it becomes stabilizing effect. It will make the growth rate smaller. And if the Lewis number is negative, then it becomes, then it grows. I mean, then the whole thing becomes positive, and it leads to an instability. But what's important here, and that's the only thing new on this slide, is what are the parameters that appear? That's really the beauty always of analytic analysis. You can look at what parameters are important. And you have 3 parameters. First is the expansion ratio, the density ratio over the flame. The second one here is, let's say, the Lewis number, and here we evaluate what's called the effective Lewis number. And then the third is here the Zeldovich number. And the Zeldovich number, in a way, is a non-dimensional activation energy. So these 3 are the important parameters, and nothing else, by the way. I mean, these are the parameters. That's it. Okay. Now, this is all based on one-step global reaction. It doesn't consider multi-step chemistry, but it turns out that this, for this phenomenon, maybe it's not such a bad assumption. I mean, the details of the flame structure, they don't seem to matter all that much. This then shows experiments here for methane, hydrogen, stoichiometric hydrogen, and lean hydrogen. Just to show you these differences, methane has no instability. And then if I look at a stoichiometric hydrogen flame, then you see this is 0, and you shouldn't get a thermodiffusive instability, let's say. But you see you get some instability, but it's very weak. You look at the perimeter of this sphere, then it's very smooth. And you see, so this is just a hydrodynamic instability. We'll see later on, the hydrodynamic instability doesn't really make the flame go much faster. I mean, it has not much of an influence. And then here for lean flame, you get thermodiffusive and hydrodynamic instability, and then you see also on the perimeter that there's a strong instability, and that really changes things a lot. We look at this for laminar and turbulent combustion. We start with the laminar flames, and we start out with a linear analysis. Okay, what means linear analysis? It means the perturbation is so small that all nonlinear effects don't play a role yet. I mean, that's like in the linear stability analysis where all nonlinear effects go away. And so we study this here not by doing, analysis with pencil and paper where you need to make a lot of assumptions. Here we study this by doing numerical simulation. And that's actually quite straightforward to do this. You just define yourself a domain, computational domain. We initialize this with burnt and unburnt mixture. I mean, here basically just with a laminar unstretched premixed flame. And then you see we put a very little perturbation, a little wave on top of this. Very, very small. In fact, here we zoom into this region and, then this is how this looks like. And that has a defined wavelength and a very small amplitude. And then we just let the simulation go. And we know from the linear stability analysis, we know that if it grows, then it should be an exponential growth. So we look at the amplitude as function of time. You see this here. This is the amplitude as this is of course all full field. I mean, this just shows one isocontour. We see how this grows as function of time, and we fit it to an exponential growth, and from that we get the growth rate. Okay, so it's all computational. And then we do this for all possible wavelengths, and then this is what you get, the individual points, and you get a dispersion relation like this, growth rate as function of the wave number, or here the 1 over the wavelength. And then we said earlier, this growth rate is actually the combination of the hydrodynamic instability, which is always there, and the thermodiffusive, but we said the hydrodynamic instability is just proportional to the wave number. And because we're in the linear regime, these two, they should superpose, right? And so we can just subtract this growth rate from the total growth rate, and that gives us then the growth rate only of the thermodiffusive instability. Okay, so this is what you get, and there are a few things that are interesting here. What we see is that the diffusive effect, it depends, of course, on the wave number, on the wavelength, and it becomes stabilizing as soon as the wavelength is smaller than 3 times the flame thickness. So if the wavelength is too small, then it doesn't do very much anymore, and the diffusive effect becomes stabilizing. The growth rate is negative, right? And also what we see is the maximum growth rate is roughly at about 6 times the flame thickness. Okay, that's something we can keep in mind. Okay, and then we can do all sorts of analysis. I mean, we can do this for different equivalence ratios, temperatures, pressures, and so on. We can do this for all these different conditions and see what we get, and we don't need to discuss the details. What's interesting to note is the instability gets stronger if you either decrease the equivalence ratio, you make it leaner, or if you increase the pressure, or if you decrease the temperature. Okay, so high temperature makes the instability go away. High pressure makes it stronger. And then we can look at the individual parameters. We set the Zeldovich number, the density ratio, and the effective Lewis number were important parameters. Interesting, if we change the pressure, we don't really change the Lewis number, we only change the Zeldovich number. If we change the temperature, we change the density ratio also, and things like this. We can fit the growth rates as function of these parameters, and then we kind of see how important each one is. And so, these are the coefficients here, and you see here, for example, that Lewis number is very important. They're all very important in a way, but the density ratio in combustion usually doesn't change all that much. Whereas here, for example, especially for the pressure, it's all the Zeldovich number that makes the change. Okay, so then this was the linear regime, okay? And now we can look at the nonlinear regime. Now, what we do is we just before we put in a very, very tiny perturbation and we watch it grow, but only over a time where it's still very, very small. But now we let it grow into the nonlinear regime. And this shows an experiment that does that. This is a Healy-Shaw cell. So these are 2 plates which are very close to each other. They form a very small channel. It's filled with a few layer mixture. There's a wire here that ignites the mixture. And then you see that you form these instabilities. It's not a flat front that burns down. You form these instabilities. And then we do the same thing here in the simulation. We do 2D simulation. It's burned on top, unburned on the bottom. Is a hydrogen-air mixture, equivalence ratio 0.4, otherwise standard conditions. Turns out these are quite expensive, these simulation. We have a small inflow here to keep the flame in the domain. The flame wants to burn down. We have an inflow to keep the flame inside the domain. We put a small perturbation here, but it doesn't really matter what the perturbation is. We probably here use the maximum growth rate, the wavelength of the maximum growth rate, just to go fast into the nonlinear regime. And then you see here how this works. First it looks periodic even, and then it becomes chaotic, and you see these structures moving around and, you know, forming, we discussed this before, forming these fingers here, forming these regions of very lean mixture here in the trailing region, and so on. And so now, you know, first of all, compare this with the experiment, and you see the experiment, they show very similar structures compared to what we have in the simulation, and that, in a way, should be expected. So now what we can do is we can look at different aspects. The first one is an interesting question. That's really why we did the simulation. People have done these simulations before, but they found that the largest structure, the finger you see, it's proportional to the domain size. And we are wondering, is this only because the domain size was too small, you know, or does it always grow with the domain size? And so we did simulation with larger and larger and larger domain. And so that's what you see here. So this here shows the domain size in units of flame thickness. This is log 10, so this here would be 10. This is 100, and this is 1,000. And then this is the consumption speed, the overall consumption speed, you see, you know, divided by the laminar consumption speed. And for very small domain size, it's just a laminar flame. It doesn't even get unstable. And then you get a jump where it gets unstable. And then it still keeps growing. But when you are about at 100 flame thicknesses wide, then, you know, it becomes independent. So there is a largest size of these flame fingers. It turns out, of these large structures, it turns out it is about 25 flame thicknesses, and then it doesn't grow anymore. Okay, so we need a domain size of at least 100 flame thicknesses to become independent of the domain size. Then we can look at you know, the size of these structures. So here we just evaluate the curvature, and you see you always get these peaks of curvature, and one cusp then is just, you know, the length is just from one peak to the next. We can evaluate these, look at a PDF, and what's interesting here, the maximum or the highest value in the PDF, the most probable size, is 6 times the flame thickness, and that was the size of the maximum linear growth rate, right? And so turns out these start growing at that size because they have the largest growth rate, and then they combine later on together to form these larger scale structures. And a few other things that one can learn from this. Now we can do these simulations also for many different conditions, just like we did in the linear regime. So this here shows the reference case, and this shows just a higher temperature. And you see high temperature, you know, makes the instability much, much weaker. This here has higher equivalence ratio, makes it also weaker. And this here is higher pressure, and you kind of see, you know, the instabilities get stronger even for this. And we can do this then for, you know, many different equivalence ratio, temperature, and pressure. And the findings are the same as what we had in the linear regime. You know, that leaner, low temperature, and high pressure makes the instability stronger. This then shows the results for, you know, different equivalence ratio, temperature, pressure, and so on. But we don't want to go through these in detail. I just want to show you, discuss one single case. And for this one single case, the question is, you know, what makes the, I mean, first of all, how fast is the flame? And then what makes the flame fast? So let's just look at the reference case here. This is, you know, ambient temperature and pressure. And this is an equivalence ratio of 0.4. That's what we often use as a reference. And it turns out this blue line here shows the consumption speed divided by the laminar flame speed. So this flame burns 4 times faster. What's the consumption speed? Is basically the speed a flat flame would have to burn the same mass of fuel, you know, in the same time, right? And here, you know, it's not flat, and it doesn't burn necessarily with a laminar, unstretched flame speed. You know, you have larger surface area, which makes it faster. And you have, maybe locally, it burns faster or slower because of stretch or whatever, right? So that's what we can look at here. We say the consumption speed is the increase in flame area times the increase in the stretch factor. Stretch factor, again, it just means how fast does the flame burn locally compared, what's the flame speed locally compared with the unstretched value, okay? And that, so this times this must be, you know, the total value. Total value is 4, and we see here for this reference case, each one of these is a factor of 2. So this has twice the surface area, and it burns locally twice as fast as the as an unstretched laminar flame. Okay, and then you know the different parameters, they give you some different stuff. But both flame surface and local reactivity are important. And then here's an interesting thing. Now we have looked at the instability in the linear regime and in a fully nonlinear regime. In a linear regime, you know, we just had a little wave that grows. Nonlinear regime, we had very chaotic structures, blah, blah. I mean, very, very complex, right? Now, we did these simulations for many different temperature-pressure equivalence ratio, both, right? So in the linear regime, for each temperature-pressure equivalence ratio, I get a certain growth rate. And in the nonlinear regime, we evaluated the consumption speed, right? And now, I can, for each condition, I can plot the consumption speed I got in the nonlinear regime over the growth rate I got in the linear regime. And the question is, you know, are they correlated or not? And you see you get a perfect correlation. Now that is interesting because it means, you know, what I get in the linear regime can already tell me what will happen in the nonlinear regime. But the nonlinear regime is so chaotic and complex. How is that possible? Any ideas? I mean, do you see the puzzling point? You know, this little growing wave already tells me how fast this thing will burn. You know, even though it's chaotic and blah, blah. It has locally rich, lean mixtures. You have all these wrinkles and... Okay, that's what I said some time ago. As engineers, what do we do? What do we like best? Sorry? Yeah, linear. He says linear. No, we like nonlinear stuff. I like nonlinear stuff. But, you know, when we analyze, what is the first thing we always do? Are you guys all engineers? Any non-engineers here? No. Okay, okay. Engineers. I'm glad we don't have chemists because they don't. So it's dimension analysis. That's the first thing we do. You know, Kármán's famous law of the wall, dimension analysis. Kolmogorov's -5/3 law, dimension analysis. You know, it's all dimension analysis. We said the only 3 parameters that appear for this instability are the Zeldovich number, the Lewis number, and the density ratio. And these are in both cases the same. And if they're the same, you know, I mean, they should be correlated, right? There's nothing else that can be different influencing them. So that's very interesting. Dimension analysis would have told us this, but I was surprised for a minute, you know, when I first saw this. Anyways, we can fit this now also, here the consumption speed. We can fit this with pressure, temperature equivalence ratio, and this is the quality of the model. And then you can use this. Actually, when you do a simulation, you can just put in this, this thing. 5 minutes, huh? Okay, so that might be a useful fit or not. Now, what's interesting is we can ask the question, you know, all of this, how is this influenced by the thermodiffusive instability? How is it influenced by the hydrodynamic instability? And I said earlier, we know that the hydrodynamic instability doesn't have much of an influence. In fact, it turns out, and maybe I can see this here, this is the consumption speed that you get only from the hydrodynamic instability This only from the thermodiffusive, and this is the total. It was a factor of 4, as we said earlier. And you see here, the hydrodynamic instability gives you maybe 30%, so it's 1.3, and this here gives you a factor of 2. So the total should be 1.3 times 2, but it's much more. 4 is much more than that, okay? So the point is, you get, if you put them together, you get a nonlinear enhancement of both, okay? So when the hydrodynamic and the thermodiffusive, they work together, they give you more than only this times only that, okay? So there's a nonlinear interaction. That's maybe all I say about this without going into details because we have only a few more minutes. Another interesting question is, I showed you all these simulations in 2D. You know, is it valid only also in 3D? And so we did 3D simulations. We did only one, actually, because this simulation here costs as much as a big DNS. 1.6 billion grid points and so on. So it's a laminar flame, but it's super expensive to do it. And but we compare. Here's the 3D result. So first of all, interesting. You know, this is how these flames look like when we looked at it earlier. This is the 3D, and the 3D looks totally different from the 2D. But if I take just a slice out of the 3D and compare it with the 2D, then they look very similar, right? And so what we saw is that actually all the flame states, I mean, if I look at the local state inside the flame, they're very similar, only that the 3D, it gives you much more of these rich and much more of these leaner mixtures, you know, because why? Because a curvature in 3D is always higher than in 2D. Right? If I have a curvature in 2D, it's like it's like a barrel, it's like a cylinder, right? But in 3D, it's more like a sphere. So 3D has higher curvature than 2D, even if they are, even if a slice of it is the same. So that's why you get more of this. I want to show you one example here of a turbulent case, maybe, before I stop. And that is, that's this example here. Yeah, this example. That's a, oops, sorry. Yeah, this is a nice example. So this answers two questions. First of all, how important is this when you have a turbulent flow? Because in a turbulent scenario, usually we say molecular effects, they're not important anymore. Diffusion is a molecular effect. You could say maybe it goes away. What we will see is that it becomes even stronger, okay? The turbulence makes the effect even stronger than in a laminar flame. And the second question one could ask is, we said, for high temperature, for high pressure, the instability gets stronger, but for high temperature, it gets weaker. Temperature effects are usually exponential, you know, and so they might be dominating. And now in an engine, internal combustion engine, gas turbine engine, I usually have isentropic compression, so I get high temperature, high pressure. You know, high pressure makes it stronger, high temperature makes it weaker. Which one wins? Okay. So here we did simulations of a flame kernel inside an internal combustion engine, and the flame kernel is, you know, initially very small, just after the spark, and then we see how it grows. The conditions are 800 Kelvin, 40 bar. This is what you would have maybe in an engine with a compression ratio of 14. And then we will look at the laminar case. Then the consumption speed divided by the laminar flame speed is 1.7. Okay, so it's very, as I said earlier, you go to a high temperature, high pressure. Earlier we said at reference condition it was 4. High temperature, high pressure, it's only 1.7, okay? So it's not very strong. Okay, so we do these simulations, we do 3 simulations. One is a real hydrogen kernel. One is the same, but we set the Lewis number equal to 1, just to see what's the effect of the Lewis number. And it's all in turbulence, it's all in a turbulent flow. And the third one here, is not with a turbulent flow. It's just a laminar flame kernel at the same conditions. You see the laminar flame kernel, it actually takes some time until it reaches what is called the critical radius, and then it becomes unstable, forms these cellular structures. You see the laminar, the Lewis number equal to 1 kernel, it grows very slowly, and the real hydrogen kernel, it grows much, much faster than this. Okay, so why? Because of the Lewis number. The only difference here is the Lewis number. And what's interesting is what we saw in these kernels also, we did similar simulations for isooctane. You see in the beginning, the turbulence squeezes this kernel so that it really has a lot of high positive curvature, but high positive curvature burns much faster in, for hydrogen than negative curvature, so that's actually very good. Okay, so the reason why this, and also you see the transition to a fully unstable flame happens much, much earlier than for this case where we have no turbulence. So the mechanism is this: the turbulence in the beginning, it just squeezes this kernel. It makes it like a pancake. But pancakes have on the edge, have very high positive curvature. Very high positive curvature means now this instability, it burns really, really fast. And so you see here on the surface also the reactivity, and again, you see this sometimes very high in the positive region and very low in the negative region. If we look at this quantitatively, this is the consumption speed as a function of time, and you see this is the laminar kernel. It also burns faster than the laminar flame because of the curvature effect. It's just a stretch. But you see the Lewis number equal to 1 kernel is not much faster than the laminar kernel, but the turbulent, unstable kernel here is about 4 or 5 times faster than the other flame. Okay, so in the laminar case, the instability made it about twice faster. For the turbulent case, 4 to 5 times faster. Okay? So why is that? We can again look at the stretch factor and the global wrinkling. If we see the global wrinkling doesn't really make a difference here. But the stretch factor is 4 times faster than the unstretched flame. Okay? So this flame locally burns 4 times faster because of the effect of the instability. Yeah. So that, and then there's some more about modeling, but you can look through the slides. No, I say, one more thing and then I stop, okay? I mean, now we have developed here a FlameLab model, and it doesn't matter how it looks like. It's described here in this paper a long time ago here by my former student, Guillaume Blancard, and now his student, or not his student anymore. But anyway, so we have developed this model, and we tested it with an optimal estimator method, and we saw the error here is almost 0. Okay, so it's a really good model a priori. If I just test it using DNS data, and then we put it in a simulation, and this is the DNS. This is the a posteriori LES of the same case, using some model, a single FlameLab model, not very good, okay? Using a single FlameLab model, but now we take I naught, from the function I showed you earlier, from the laminar flames, also not very good. Then we use the FlameLab model we have developed, where the progress variable is hydrogen, which is what we had proposed a long time ago, and it's shorter. Actually, flame length is not so bad, but you see these super equilibrium temperatures we can predict. And then use this, but now with hydrogen, water as a progress variable, it's better, but it's still not perfect, okay? So that's currently the state where we are. We're trying to improve these models. Okay, so with this I'll stop. Thanks everyone for coming here to the lectures, for being attentive and for asking all the questions. Remember, most of you are PhD students. If you finish your PhD, you're looking for a postdoc position in the most beautiful city in the world, in Aachen, then, let us know. Okay, thanks again, and all the best.